Welcome to video 3.3 on electron configurations. In this video, we're going to understand how the electrons function within an atom in terms of their energy level and their orbitals and even their suborbitals. Also in this video, we're going to focus on the electron configuration. Electron configuration is the idea of expressing how electrons are arranged within an atom. We're also going to learn how to write out the orbital notation. The orbital notation is very similar to the electron configuration, it just gives a little more detail. And finally, you'll also learn how to do the noble gas notation in this video as well, which is given to you in your periodic table, which you will see all three represent the same thing. They're very similar. It's just some slight tweaks that we would do to each of them. The last thing we're going to do in this video is we're going to use the electron configuration and the noble gas notation to determine the valence electrons within an atom. The valence electrons are considered to be the electrons that are used in bonding and often considered the electrons in the outermost energy level. So as we get started, here are your vocabulary terms. Again, if any time you don't understand a word or a concept, feel free to pause the video, Google it, take a quick peek at it, but a lot of these are defined within this video. So the electron arrangements. We know that atoms have protons, neutrons, and electrons. We know the protons and neutrons are in the center at the nucleus, and we know the electrons fill up the empty space outside the nucleus, and they take most of the volume within an atom. Our electron configuration is a way to write out and to describe more information and more detail about where those electrons are and where they exist at. The electron configuration is going to include energy levels and orbitals. Remember, we already talked about in class that the orbitals we're covering are the s orbital, the p orbital, the d orbital, and the f orbital. So the electron configuration is the way we write this out, showing all this information in a very orderly way, and it also is a way for us to see how each element has its own specific and unique electron configuration. Now, electron configuration is going to be very similar. They're all going to have a lot of the same beginnings and start, but the end product will be slightly different because each element typically has a different number of electrons. So if you have not already, pause the video and get out your periodic table that I gave you in class. That looks like this. So as I begin to show you, in a minute I'm just going to show you a couple examples of the electron configuration. But as we get started, the first thing I want you to do is have the mindset that just watch the pattern. Watch the pattern and the thought process that I go through to write out the electron configurations. Your periodic table is going to walk you through writing out these configurations. And I already told you that the configuration is already actually given to you on the periodic table, meaning the answer is already right here. But you have to learn how to read the table and write these things out. And I'm going to show you how to do it, but like I said, just follow the pattern. So a few of the things I'm going to be looking for when I go to write the configuration is I'm going to be looking for their energy level. When I go to write out the electron configuration and I start with the energy level, I need to understand that the period number is actually the energy level number. So you can see here I have the numbers 1 through 7, and I asked you to already include that on your periodic table. And so as I get started, and as I start to fill up the first energy level of electrons, I'm going to realize that period 1 is the same thing as energy level 1. Period 2 is the same as energy level 2. Period 3 is the same as energy level 3. So you'll hear me interchange that out a lot. The other thing I asked you to do in class already is to write down S, P, D, and F. These blocks, imagine helium was right here, are written this way and designed this way to show us how the electrons stack up in the different orbitals. And this is considered the S block, this is considered the P block minus helium, this is considered the D block, which are also known as your transition metals, and then down here your lanthanides and actinides are considered the F block. So again, make sure you have these written on your paper. And one other tweak I want you to go ahead and do, I'll explain this when we get there, but go ahead and write D minus 1, and down here, go ahead and write F minus 2. Again, that'll make more sense when I talk about it in a little bit, but go ahead and make that update. The last little trick to do, to think about, is that the atomic number is defined by the number of protons, but since we are talking about neutral elements right now, the atomic number is also can be used to count the number of electrons. So if I ask how many electrons are in hydrogen, since that atomic number is 1, we would say there's 1 electron in hydrogen. Helium, if I ask how many electrons are in here, you can easily look at the atomic number and know there's 2 electrons in helium. So what we're going to do is we're just going to use our periodic table and we're going to fill up the electron shells. Kind of like how you fill up a glass of water, the water goes in the bottom and fills towards the top. When you fill up the electron shells or electron energy levels, you start by filling up the inner energy levels first and you move outward. So again, this is a rough model of the Bohr's diagram, but instead of doing this, we're going to actually start using the electron configuration model. So here's what I want to do for you. I want to show you how you would come up with the electron configuration for hydrogen. Now again, I already told you the answer is right there, but let's act like that answer is not there because you need to learn the process. So first of all, we understand that hydrogen has one electron. And we've already started hearing that the very first energy level there is the one energy level. So we've already called it, the first energy level is called energy level 1. And the first orbital that exists in energy level 1 is the orbital s. I can be reminded that this s is here to show me that these electrons all exist in the s orbital, but this is the path we follow. We're going to fill up the 1s orbital first. And then since hydrogen only has one electron, we're going to give him a 1 here to show the electron configuration for that one electron. There's one electron in the first energy level in the s orbital. Something I will show you again here in a minute, but it might help you guys out, is this slide here shows you all the possible energy levels and their suborbitals. So in energy level 1, you have the s orbital. In energy level 2, you have the s and the p. In energy level 3, you have the s, p, and the d. In energy level 4, you have s, p, d, and f, and then so on. So what you're seeing here is the same thing we're going to go through on this table. We're going to follow the first energy level s, then we'll go to the second energy level s, second energy level p. But as I look at hydrogen, it's 1s1. So all I'm trying to teach you to do now is come up with these electron configurations by following the periodic table. So let's do the electron configuration for helium. Helium over here has 2 electrons. We're going to pretend that helium exists in this box right here. And so if I want to fill out the electron configuration for helium, I start at the beginning. I see that I'm in the first energy level because I'm in the first period. We're dealing with the s block here because we're pretending that that's right here. And I see that there is 1, 2 electrons. 1, 2 electrons. And so therefore, the electron configuration for helium is 1s2. And again, if any time you need to, you can check your answer on your periodic table to double check that you got it right. Let's do lithium now. So as I walk along the periodic table, I just follow the path. It's going to be just like what I did up here. If I want to go to lithium and I want to do electron configuration, I'm going to write 1s2 because I got 2 electrons here. Imagine again, this was here. I have 2 electrons in the 1s block. Now I'm jumping down into the second energy level, and I'm in the s block again. Now though I'm in lithium, I only have 1 square here. So since I'm only 1 square over, I only have 1 electron in the second energy level. So therefore, I would write 1. Now let's look at boron. Boron again, I'm going to start with the 1s2, just like I did up here. Then I'm going to come and I'm going to fill up my second energy level. There's 1, 2 blocks here, meaning there's 2 electrons in the 2s orbital. And now I'm still in the second period, but now I'm in the p block. So now I'm going to call that 2p. And since I am the first box in, that's only 1 electron, I would write a 1 here. If I had carbon, I would put 2p2 for carbon. If I was at nitrogen, I would put 2p3. If I was at oxygen, I'd go 1, 2, 3, 4 blocks. I'd call that 2p4. Now let's look at one more here, fluorine. How do I write the electron configuration for fluorine? Again, I start by just filling up the layers. First layer going to get filled up is 1s2. Second layer gets filled up is 2s2. Next layer would be 2p. 2, this is still in the second period, but now I have 1, 2, 3, 4, 5 electrons here, so I would put 2p5. Again, where did that 5 come from? Because there are 5 blocks, 1, 2, 3, 4, 5, which represents 5 electrons in the p block in the second energy level. So that is how you write the electron configuration. And in a moment, I'll show you a few more that involve the D and F orbital. But right now, to get you started, this is how you write the electron configuration. Now, the next step is taking this one step deeper, and from the electron configuration to be able to write out the orbital notation. The orbital notation allows me to see what is going on inside the orbital. So when we go to write this, it's the same idea as this, but we just give a little more information. So you write it out by continuing to write the energy level first. So this is 1, first energy level. I write down the orbital still. This is S orbital, S orbital. But now below here, we're going to write down the quantum number for the possible sublevels. And I already kind of told you that in the S block, it gets to be called 0. But then when we come to write the sublevels, if I want to look at the sublevel for S, there isn't really a sublevel. There's just that one level. So we're going to have just one line and call that 0. But in a minute, we're going to get to the P, D, and F sublevels. And in a minute, I will show you how you label those out when we get there. But for right now, for orbital notation for hydrogen, all we're doing is writing down the energy level. We're writing down the S block. And then we're going to call this sublevel 0, which is the M letter for your quantum number, the magnetic quantum number. And now since I have one electron, I'm just going to draw an up arrow. This is called the orbital notation. This is called the electron configuration. This shows me what's going on inside the orbital. This shows me the number of electrons. So now let's look at helium. What is the orbital notation for helium? Well, again, I'm in the first energy level. I'm in the S block. My sublevel here is 0 because that's my M quantum number. And now I have 2 electrons. So what I'm going to do is I'm going to put 1 electron as an up arrow and 1 electron as a down arrow. Now we'll do the same thing for lithium. Orbital notation for lithium. I have 1 S, 2 electrons, and now I'm in the 2s. And there's only 1 electron here, so the first electron will always give it an upspin. Now when we get down to boron, we see now we have to start to account for the different sublevels that P has. So if I want to write the orbital notation, I again do just like I did before on the problems above. So I'm going for boron. I filled in the 2 electrons here, the 2 electrons here. There's the 2 electrons with 2 electrons. Now I need to write out the orbital notation for the 2p1. So here I'm going to write 2p, but now I have 3 sublevels. We talked about geometrically, they're called the X, Y, and Z. But in terms of the quantum numbers, and in terms of how we label them, we label this as -1, 0, +1. Now, how are you supposed to memorize that this is -1, 0, +1? Well, the formula you can follow to find out your sublevels is you just take the absolute value of your S, P, D, and F, and then you look at the range of the whole number. So I take the absolute value, and what are all the whole numbers in that absolute value range? Meaning, absolute value 1 could mean 1. It also includes 0 in that range and +1. So when I look at D, I take the absolute value of D, and I see that my sublevels that you're going to get to when we get to the D would be -2, -1, 0, +1, +2. When I look at F, F is 3, so what's the range of the absolute value of 3? And these sublevels are labeled as -3, -2, -1, 0, +1, +2, and +3. Again, these numbers represent the different geometrical paths and dimensions that they exist in. But for quantum numbers, we use these values, and they come back from the absolute value ranges of the sublevels up here. So again, as I look at my sublevels here for 2p, I see that I have just 1 electron, and we're just going to fill in that first arrow. And that, again, is how you do the orbital notation for boron. So now let me do one more with fluorine, and let me show you 3 more things you want to pay attention to when you're filling up, not the glass, but when you're filling up these orbitals and energy levels. And there's some rules and principles that you got to know academically, the name and who came up with them. So first of all, for fluorine, if I want to write out the orbital rotation, I need to go back to the beginning, and I need to turn my 1s2 into the orbital rotation. So I go 1s, 0, 2 electrons, electron up, electron down. 2s2. Again, that sublevel is called 0 because that's all s has. Electron up, electron down. Now I'm into 2p. Again, here I have 3 sublevels, -1, 0, +1. How did I know that? It's the absolute value range of that, which is -1, 0, +1. And now I have to start filling in these 5 electrons. So here's the way you should practice filling these in, and that's because there's rules and laws behind how the electrons behave. When you have these 5 electrons, I want you to get in the habit of filling them in by spreading these electrons out. So I need 5 total, so there's 5 total, so I did 1, 2, 3. So notice how I filled it in by putting 1 here, 1 here, 1 here, all with the up spin. Now I'm allowed to come back and pair them up. And then since there's 5 electrons, that's why I drove 1, 2, 3, 4, 5 arrows. That's why I drew 5 arrows. So why did I show you that? Why did I show you to write your orbital rotation by spreading these arrows out first and then coming back after filling up each individual suborbital and then come back and double up your arrows? Here's why. We have these things called principles and rules that Aufbau, Pauli, and Hund came up to. These are things that you need to know academically, and I'll kind of breeze through them real quick. So the Aufbau principle is kind of like the filling up a glass rule. The Aufbau principle just says the electrons will occupy the lowest possible energy level it can. So again, why do we keep starting with 1s? Because of Aufbau's principle. Whenever you get an electron, he's automatically going to fill up this first inner lowest energy level and orbital. So this is actually an energy chart. So these guys have the lowest energy. These guys have the highest energy in terms of how much energy it takes for them to be away from the nucleus. So again, this follows our periodic table. When I look at my periodic table, that's why we go 1s to 2s to 2p to 3s to 3p to 4s. That's why we do that, because of this energy chart and the way it follows the periodic table. The next rule I want you to see is the Pauli exclusion principle. Pauli exclusion principle says that no 2 electrons can have the same 4 quantum numbers, meaning they have to have different addresses. That is why it's important to make sure you have up and down arrows. If I were to put an up arrow and an up arrow and an up arrow here, then their quantum numbers would all be exactly the same, and Pauli says that can't be true. I need to show the down arrow here to show a difference between this orange electron and this blue electron. So Pauli just simply says that electrons cannot have the same 4 quantum numbers, meaning that they both can't be positive spins and they both can't be negative spins. They have to be opposite. And then Hund's rule says that orbitals or electrons in the orbitals of the same energy level will occupy 1 electron before they start to pair up. So why did I go back and why did I make such a note to show you that these electrons spread out before I went and added the 4th and the 5th down arrow on fluorine? Because I want to show you Hund's rule, that he kind of says the same thing like when you're living at your house. If you have a 4-bedroom house and you have 2 siblings, of course your parents are going to take a bedroom, but you and your siblings are not going to share a room if you don't have to. There's 3 of them bedrooms, you and your 3 siblings will each get your own room. But once that 4th unexpected sibling comes along, then somebody has to bunk up. And that's what Hund says. He says the electrons want to spread out. They're all the same negative charge, so they want to spread out as much as possible, and they will occupy their each individual suborbitals until they are forced to pair up. And that's what Hund says. And that's why when you go and you fill this out, I really encourage you to get in a habit of doing something like this, where you fill in your electrons by putting up arrows first and then come back and pair them up. That way you avoid running into getting something wrong like this. All right, so let's practice real quick. Why don't you go ahead and pause the video. You guys try this real quick. Go ahead and try to do the electron configuration for hydrogen, for helium, for lithium, and for fluorine. Try those by yourself. So pause the video, try those real quick, and then come back and watch me do it. And then wait, and we'll do chromium together. Go for it. All right, so hydrogen, I already showed you how to do this one, but I'll do it again just because it doesn't hurt. Hydrogen, first, there's one electron. Where does that one electron go? He goes in the first energy level. Oh, I gotta show this over here to you. Okay, so hydrogen, first one electron. We see it here. He's in the first energy level. He's in the s orbital, and there's just one block here. So that means there's just one electron that goes there. That is the electron configuration. Now to do the orbital notation, you should have just translated that into this. Again, one up arrow. First energy level, S block. The sublevel here is 0. Again, if you need to, write this down that S, P, D, and F are 0, 1, 2, and 3. And then if I want to do sublevels, it's the absolute value range. And so if I want to do the absolute value range of P, it's going to be -1, 0, +1. So again, this is your S, this is your P, and then your D, which we'll see here in a little bit, is the absolute value range of 2. It's -2, -1, 0, +1, +2. All right, so that is the orbital notation. That's electron configuration. Helium, same idea. 2 electrons. These 2 electrons are in the first period, meaning they're in the first energy level. They're in the S block. And there's 2 electrons. Draw it like this, bada bing, bada boom. Lithium, 3 electrons. First 2 electrons are in the 1s energy level. That third electron's in the second energy level, and there's just 1 there. How do I write this as orbital notation? It goes like that. First electron in second energy level, so it's only going to get an upspin. Now again, fluorine, again, you saw me do this earlier, but I'll show you again. We're going to follow the same filling pattern we've done all along. Now we get to the 2p. How many electrons are in that p block? 1, 2, 3, 4, 5. There's only 5 electrons in 2p5. There you go. How do I show this in orbital notation? 1s naught, up and down, 2s naught, which is nowhere for 0, and then 2p. And now here's where you want to pay attention on how we put in these arrows. Again, what are my sublevels or P? They're called -1, they're called 0, they're called +1. Now I have 5 electrons to fill in. Bam, 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 following Hund's rule. Now I come back and pair up there. Quick side note, if I want to do the quantum numbers for this last electron, what would it be? Again, the N says it's in the second energy level. The L is in the P, so our P is 1, so the L would be 1. The M is that sublevel, so it's 0 because it's in the middle there, it's on that y-axis. And then the spin, which was S, so it's a down arrow, it would be a -0.5. That's your quantum number practice. Okay, now let's look at chromium together. So chromium is here with electrons 24. The first 3 energy levels are going to be exactly like what you just did with fluorine. So let's go ahead and do that. So we got chromium right here, Cr. So the orbital notation, I would write 1s2, check, 1s, there's 2, 2s2, 2s12, 2sp, 1, 2, 3, 4, 5, 6, so it's 2p6. Now we're jumping down here to 3s2. Now we're jumping over to 3p, 1, 2, 3, 4, 5, 6. There's 6 electrons in 3p, so we have 3p6. So now I am right here on my periodic table, and I am going here to chromium. So what do I see next? These 2 electrons, electron 19 and 20, are in the 4th energy level, and they're still in the s block. So I'm going to write 4s2. Now we are, however, going to enter into the d block. Here's where a curveball gets thrown. This D block appears to be in the 4th energy level, and that's what you expect. However, when you look at the energy chart, here, we see that that D block actually has a slightly lower energy level than the 4p, and it's slightly above the 4s, but we consider that the 3rd energy level. So long story short, because of the actual energy reading and because of whatever reason in science, I had you write down this D-1. So whenever you come into the D block, you're actually going to subtract 1 from that period number. So when I go from 4s2, I'm actually going to 3d1, 3d2, 3d3, 3d4. So your correct answer here would be 3d4. If you ever want to, sorry, that should be a little superscript. If you ever want to double check yourself, you can look down here. Now, as I look here, I see the answer is actually slightly off. The key says 3d5 4s1. And chromium here is actually now just doing some unusual behavior. And I'll show you why that is when I write out the orbital notation. So the idea here is if I was to write this out with orbital notation, again, I would start with 1s naught, 2s naught, 2p, and I got my 3 blocks. I'm going to go 6 electrons here, 2p6. I'm going to go to 3s2. Then I'm going to go to 3p again. And again, you can see this is not challenging. It just sometimes takes a lot of writing. I have 6 electrons here, so I got to make sure I fill this with all 6 electrons. Now I'm going to 4s. And now we expected to fill the 4s here first. Then we expected to get to our 3d. 3d suborbitals, how would I call those? Again, that's -2, -1, 0, +1, +2. So I'd call that -2, -1, 0, +1, +2. We would expect this to be the case for chromium because of what Aufbau says. Aufbau says that they're going to fill the lowest energy level first. Well, here's just an exception to the rule. And you might ask, well, how do I know when there's exceptions to the rules? Well, I already gave you the answer. You just got to be aware that every now and then there's an exception to the rule. And this kind of makes sense. Why does chromium, instead of being called 4s2, 3d4, why does my periodic table say he wants to be called 3d5, 4s1? Why is this 1s electron seem to jump ship over here? Well, same reason why you would probably be willing to take an extra bedroom in the basement of your house. You can either share a bedroom with your sibling on the first floor, or you can maybe go upstairs or go down to the basement and have your own bedroom with a very little additional energy put out. So because, if we go back and look at this energy chart, we see that because the 4s and the 3d energies are so similar, that an electron, because of repulsion, would push away from this one electron and would rather fill up this last orbital here by himself than to be stuck sharing a room or sharing an orbital in the 4-1s. So again, this is just an exception you might see as you move down the road. But again, like I said, how do you know when those exceptions pop up? Because your periodic table will tell you, and it will kind of give you where it doesn't follow the pattern like you would have expected to do. So again, that would have been an exception. All right, so let's begin to move on a little bit. So again, I've already covered the Aufbau principle, saying that electrons will fill the lowest possible level it can. Again, every now and then there's exceptions where instead of pairing up in 4s, that one electron will jump over here. We've also seen that Pauli exclusion principle says that we have to have a positive spin and negative spin, that 2 electrons cannot have the same 4 quantum numbers, can't have the same address. We also see Hund's rule, where it says that these guys will spread out individually first before they bunk up. So here is the practice problems you just did. Now I got one more notation to show you, and it's called the noble gas notation. Noble gases are the things that exist in that 18th family, or that 8th family, however you want to call it. These noble gas families actually have full energy shells. So when I have helium here, he actually filled up the entire s orbital. When I have neon's electrons all filled in, he actually filled up the entire second energy level. So 2s and 2p were completely filled with electrons. So since these guys are stable because they fill up these electron shells, we can use these as like starting points, or basically shorthand ways or shortcuts in writing out our noble gas configuration. So if you look at something like silver here, I could go through, and just like I did for chromium, I could go through and write down the 1s2, 2s2, and all the way out to my 4d9. But who has the time to write this out over and over again all the time? So instead, we learn to write the noble gas notation where we just go back on the periodic table. So if I want to write the noble gas notation for silver, I have to go to the previous noble gas. I just write that down in brackets. And then from there, I just pick up on my trends. So from chromium, or from krypton, we would go 5s2. Then we go into our 4d, because remember, d gets subtracted from 1. So instead of calling this 5d, we're going to call this 4d. And we go 1, 2, 3, 4, 5, 6, 7, 8, 9. And so again, that's why we were able to do that. So the noble gas notation, it's a pretty easy shortcut. The answer is given to you in your periodic table. But instead of writing out what you see here underlined in red, we just replace that with the noble gas that has that exact same notation, and then we just show the electrons after it. And again, this is just another way to do it. So we just use a previous noble gas and then start with our trends right after that. All right, so now let's practice again. Pause the video, do a really long, nasty one all by yourself. I'm not going to have you do the orbital notation because that, again, it just would be ridiculously hard, not hard, but tedious. But go ahead and pause the video and find iridium. I'll give you a hint. Iridium is number 77 on your periodic table. But go ahead and try to start from the 1s2 and fill it all the way up using your periodic table. And then when you're done, try writing the noble gas notation. And then when you're done with that, check your answer on your periodic table. And then press play again, and I'll show you the answer. Okay, so for sake of time, I already just have the answer written out here. And I want to just remind you again, iridium has the atomic number 77, meaning there's 77 electrons. So if I went through and counted up all these little superscripts, I would get 77 electrons. So how did you do it? Well, you just followed your periodic table and you filled in all these electrons as you went. So here's my iridium. Iridium is all the way down here, number 77. So I have to fill up all the energy levels and all the orbitals until I get down to iridium. So again, the first thing I write down is 1s2. Then I write down 2s2. Then I go to 2p6. Then I go to 3s2. Then I go to 3p6. Then I go to 4s2. And then again, from 4s, we jump down to 3d because of that d minus 1, because of that idea that d jumps back down to the third energy level. Then we jump back up to the 4p6. Then we come to 5s2. Then we fill in our 4d10. Then we jump back up to 5p6. Now we go to 6s2. And now here's where we want to be really careful to follow our periodic table. So as you look down here, you will see this star. That star reminds you you're supposed to jump down here to this family, or this period down here, which starts at the top of number 58. And so this is where now you're going to include the F block. Just like before when you wrote D minus 1, go ahead and write F minus 2. F minus 2 tells me that, yes, this 58 belongs to 57. Yes, you would think this is the 6th period, but it's really going to be considered the 6th period. Yes, you would consider 58 right here, and this is the 6th period. But really, we're going to call that the 4F because we're going to do F minus 2. So I go F minus 14. How did I know there's 14 electrons in F? I went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And then to get to iridium, I jump back up here and I do my 7 D block electrons. 1, 2, 3, 4, 5, 6, 7. And that got me to iridium. If I wanted to write this in noble gas configuration, I find iridium, I find the previous noble gas, and then I just start from there. After that, I'm going to go to 6s2. Again, your periodic table likes to write it this way. I don't care if this goes here. It doesn't really matter to me. It's all the same. I tend to follow the periodic table. Your periodic table likes to put the numbers first. Whatever you want to do is fine with me. But after xenon, we jump down to 6s2. After 6s2, we jump down to 4f14. And after 4f14, we jump back up to 5d. And we go 1, 2, 3, 4, 5, 6, 7. Got it. All right, so now the last thing I want to show you, and this is the easiest thing of them all, is this idea of valence electrons. Valence electrons are just the electrons in the outermost shell. They're the electrons on the outermost shell of the atom. These electrons are the ones that are involved in chemical bonding. And so when we do the noble gas notation, it's an easy way to show us who our valence electrons are. So if I go back here and I look at one of the previous problems that we did, if I was to write these in noble gas notation, it is written in a way to show me just the valence electron. If I want to write boron in the noble gas notation, it would be this. So the easy way to find out how many valence electrons there are in any given atom, sorry, it's a 5, is you just add up the individual electrons after your noble gas notation. Or you just look for the highest energy level. So here's my 2 energy level, and you just count up all the electrons that are in that highest energy level. So again, your valence electrons are just the electrons in the highest energy level that you wrote down. Your number is going to be between 1 and 8. You cannot have any valence electron numbers between less than 1 or more than 8. So your valence electron answer will always be between 1 and 8. And again, the answer is given to you on your periodic table. If you look here at lithium, it tells you the 2s1 says there's only 1 electron right here in lithium. If I look at fluorine, I have 1, 2, 3, 4, 5, 6, 7 electrons in that second energy level, and that means there's 7 valence electrons in fluorine. Nitrogen. Go ahead and tell me, how many valence electrons do you think are in nitrogen? And the answer is 5. 1, 2, 3, 4, 5. So again, we'll look at that more in class. That's the easiest idea there is. But again, valence electrons are just the electrons in the outer energy level. So if I look here at silver, how many valence electrons does silver have? Well, I see that the 5 here is the highest energy level, and there's only 2 electrons in the 5th energy level. So silver would have 2 valence electrons. All right, so I hope this video helped. Sorry it was a little long. But again, what are we doing? Electrons are going to fill up that lowest energy level first. That's called the Aufbau Principle. There are multiple ways to show electron configuration. There's 3 ways to be exact. There's the electron configuration notation, there's the orbital notation, and there's the noble gas notation. And then from this, we can easily calculate the number of valence electrons by simply looking at how many electrons are there in that highest energy level. Have a great day.